meeting, we discuss part 1 of the module 1, which is the about the structural design process, the design philosophies, and the relevant code provisions. So there we have discussed about the what what are the reasons why do we use structural steel for structures. What is structural design? What are the criteria for the structural design? How do we go around with the structural design process? So the iterative design procedure. What are the loads that we consider? Why do we have to consider all of those loads? Okay. And what are the design philosophies that we use during structural design? So now we will be going with part 2, which is in which we will be talking about the main material that we use in structural steel design, which is, well, structural steel. Okay. So what is steel? And so steel is an alloy made of iron, carbon, and other metals or non-metals in trace amounts. So steel is practically just a combination of iron and carbon. And then you introduce other metals, so we will list them later on, okay? In trace amounts, meaning in very, very small amounts, okay? So the carbon content of steel is usually go between 0.04% by weight up to 2% by weight. Okay, so there are many types of steel that we use. uh, However, we will only be talking about structural steel, the ones used in building construction. Okay, so it is discovered back. So during the olden times, we just use iron back then. No? However, it is discovered that adding carbon on steel on iron can improve its properties, especially its strength. No? So it is determined that carbon content of up to 0.9%, 0.90% increases hardness, tensile strength, and responsiveness to heat treatment of steel. So we will talk more about the manufacturing. So beyond that, carbon causes brittleness and loss of malleability of steel. So that's why we maintain the amount of carbon that we should add in steel. So uh, actually in steel mills, no, before they stack up on their structural steel products, they test it, no, for every batch of for every manufactured batch. So that is in order to ensure that the addition of carbon is the amount of carbon that they provide is enough, and it does not it is between the limits. Okay, so before steel is used, there are two other types of iron that they use in structures. So we have cast iron and we have the wrought iron. Excuse me. So cast iron is a ferrous metal. When we say ferrous, it contains iron. Okay. So cast iron is a ferrous metal with carbon content between 2 and 4%. So it is beyond what we use today. Okay. So cast iron is primarily composed of iron, carbon, and silicon, cast in a mold because of brittleness due to large amount of carbon. So the disadvantage of this one is that it it becomes brittle as time goes on. No? That's why cast iron declined in use. No, as structural steel is produced more. Okay. Another one is wrought iron. It is highly refined iron with slag deliberately incorporated but not in chemical union with the iron. So it's just pure iron with some slag mixed on it. No? So again, although it is strong, it is not enough for structural purposes. No? So when structural steel was developed, wrought iron also declined, was also declined in use. Okay. So what is the main composition of structural steel? So the main components of structural steel are just two, iron and carbon. So the rest are trace metals or non-metals. No? So other elements are added to improve the properties of the steel. So what are these elements? We have manganese, silicon, sulfur, aluminum, copper, lead, chromium, among others. So this one is not exhaustive. Okay, so these are just some of the chemicals that we add in order to improve the properties of structural steel. So what do these elements do to improve the properties of structural steel? So for manganese, it imparts strength and responsiveness to heat treatments, promotes hardness and uniformity of internal grain structure. It is important that the microscopic structure of steel is more or less uniform in order to ensure that the material properties that we expect of structural steel is can be attained. Uh, so for example, if you want a yield strength of this one, we need to make sure that the microstructure of that steel should be uniform in order to attain the necessary yield strength. Okay. Silicon, same general effects as manganese. Sulfur retains malleability at high temperatures and improves machinability. So it improves the flexibility of the steel to be used in high temperatures. No? So next, aluminum promotes grain size and uniformity of internal grain structure. Copper increases strength and corrosion resistance. So this is also important. No? We do not want our steel to corrode easily. Okay. Lead improves machinability without detrimental effect on mechanical properties. Chromium increases responsiveness to heat treatment and hardenability, causes retention of mechanical properties at high temperatures. Okay, so these are the trace elements that we usually add to iron and carbon in order to produce structural steel. Okay, so how do we exactly manufacture structural steel? So I will show a video presentation earlier, no, to show how structural steel is manufactured. So for now, let me just discuss some of the processes that steel mills or steel factories perform to produce steel. Okay, so manufacturing processes, we have the pig iron production. So pig iron is a solid carbonaceous material derived from destructive distillation of low ash, low sulfur bituminous coal. So the basic materials for modern steel making are iron ore, coke, and limestone. So these three. Okay, so iron ore, you mine this one. Same thing with the coke. No? So this one is where the carbon comes from. And we have the limestone. Okay, so what is the general process for the of steel making? So coke is burned as a fuel to heat the furnace, giving off carbon monoxide, which combines with the iron oxides in the ore, reducing them to metallic iron. The limestone in the furnace is used as an additional source of carbon monoxide and as a flux to combine with the infusible silica present in the ore to form fusible calcium silicate. And calcium silicate and other impurities form a slug that floats on top of the molten material at the bottom of the furnace. So this from the statements, the process is pretty much simple. No? You burn coke, you burn the you heat the the iron ore using coke, and then you introduce limestone, no? And then a slag forms, and then that's it. That would be your steel. No? So the only difference for structural steel is that you add the additional elements. No? So as you form the steel, after mixing the basic materials, you need to finish them. You need to mold them into a shape that you want. So what are the finishing processes that we usually do? So there are four. So we have rolling, extrusion, drawing, and forging. So for structural steel shapes, the most common finishing process is what we call rolling. So rolling is compressing and shaping an ingot into a useful shape by squeezing it through a succession of rollers. Each succeeding set squeezing the material smaller in cross section and closer to final shape. So we will show it later how the rolling process goes. Okay. So from a steel billet, no, you let them pass through the rollers. So the deformed steel, the raw steel will be formed into another shape depending on how the rollers are set up, and then you roll it until you get the final shape that you want. Okay. Next, we have extrusion, forcing a billet of hot plastic steel through a die of the desired shape to produce a continuous length of a material. So you have some sort of a mold. No? So next, drawing, pulling a steel through a small die to form a wire or a small rod of round, square, oval, or other cross section. So you have the molten steel, and then you let it cool a bit, and then you draw it through some sort of a hole, like a round hole, square, or oval. No? So pretty much like what you do when you get something through a very small hole, so it becomes some sort of a wire. So that's the drawing process. And lastly, forging, the forming steel by pressure or blows into a desired shape. So this one is usually used in making blades. No? So okay, so once you have the finishing process, you now have to do some heat treatment in order to to increase the grain uniformity of the material, and at the same time to improve the material properties. No? So what are these heat treatment processes? So we have normalizing. So after you finish the steel, you heat them to a temperature of about 1,500 degrees Fahrenheit or higher, and cooling several hundred degrees slowly in air to increase uniformity of grain size structure. Okay, so Next, we have the annealing. Annealing is a process of heating the metal slightly lower than for normalizing. So it's also around this one, but a bit lower. Holding it at that temperature for a proper period of time and then slowly cooling, usually in a furnace. So why do we do some annealing? So for the following reasons: to refine the grain structure, to, to soften the steel to meet definite specifications, to remove the internal stresses caused by quenching, forging, and cold working. So as you go through the finishing process and the other heat treatment processes, you introduce stresses on the material. So what happens is annealing may be able to remove some of them. Uh, Excuse me muna. Okay? Okay, mic test, mic test. Nadidinig ako. Okay. So, okay, so where are we now? So, okay. And the last reason why do we do annealing is to change ductility, toughness, electrical and magnetic properties. Because annealing also aims to refine the microstructure of the structural steel. Huh? So, yeah. So there you go. So another treatment process is quenching and also tempering. So quenching, it is a process of rapidly cooling the steel in oil, water, or brine. So brine is water with salt. Okay. From a temperature of about 15 degrees Fahrenheit to increase hardness and strength but reduces ductility and toughness. So due to this, quenching uh, results to introduction of what we call residual stresses. Okay, so residual stresses are stresses that already occur in a material even before you use it. So residual stresses are the effects of the manufacturing process of a material. No? Then lastly, we have tempering. Tempering is the process of reheating a hardened steel to about 300 to 1200 degrees Fahrenheit, holding it at that point for a time and cooling it to reduce residual stresses and also to increase ductility. Okay? So these two usually, especially uh, if you manufacture rebars, magkasama to, no? Although currently there's an issue about the rebar manufacturing process, no? Because in the NSCP code, it is assumed that rebars are manufactured, no, without these processes. However, some of the steel plants here in the Philippines already use this because it is what is practiced in the other countries. So right now, stopgap solution pa lang meron ng ASEP, which is if you have quench tempered rivers, you may use them. However, it is the responsibility of the engineer if something happens. Okay, so there's an issue with this. Although the process itself is not really bad because in structural steel, they already use this one. No? Sa rebars lang nagkakatalo kasi what happens is that nagiging masyadong malakas yung rebar to the point na nagiging brittle yung failure niya. Okay? So that's what we avoid in reinforced concrete. You don't want your steel to be too strong because otherwise it will not reach its yield strength. So meaning the failure will be compression controlled. Uh, so that's the issue with the quenching and tempering for rebars. But for structural steel, this one is pretty much normal. No? So okay, so before we proceed with the video, so we will watch this na. So Based on this, we can classify structural steel depending. So the classification of steel, it will be either according to the chemical composition, in which we will I flash it now, so this one, or according to its cross section. So we will discuss it later. Okay, so structural steel is classified according to its chemical composition into three. So we have carbon steel, high strength low alloy steel, and alloy steel. So what is carbon steel? So this is the most common steel that we use, no? Especially here in the Philippines. So carbon steel has increased carbon content, which raises yield strength but reduces ductility. So we talked about this earlier on, no? So the optimal carbon content is up to 0.9%. No? Beyond that, brittleness may occur. No? So carbon steel is classified further into four subtypes. We have low carbon, mild carbon, medium, and high carbon. So it depends on the amount of the carbon steel. No? So one example of this would be of carbon steel would be ASTM A36 with the properties below. So this one, I'm not really sure where does A36 belong among these four. No? I have not read the ASTM standard for this, so you may check it out. Okay. Next, high strength low alloy steel. So the main advantage of this over the carbon steel is that excuse me, is that it has a higher yield strength compared to carbon steel. So ASTM 36, if you see the table right here, the yield strength is around 36 KSI. While for the high strength low alloy, the usual range is around 40 to 70 KSI. Okay? So it has increased strength obtained from finer microstructure during the cooling process. So the heat treatment for high strength low alloy steel is pretty much different from that of the carbon steel. So the process is much more intricate, just to attain this the additional strength. So examples of high strength low alloy steel are ASTM A572, so we have this one, and ASTM A992. So A572, I think it is also available here, but the use is not much popular compared to A36. In the Philippines, we use A36 much more than A572. A992, this is the usual grade, the usual steel in the United States. In the Philippines, I don't know if our plants produce A992. No? As far as I know, the usual steel that we produce are A36 and A572. So these two. Okay. And then lastly, we have the alloy steel. So this is just a more improved version of this high strength low alloy. No? So the yield strength shoots up to 80 to 110 KSI. It has a maximum carbon content of 0.2%. So how should I say this? So the remaining content that should have been carbon, it is substituted by the other chemicals like this in order to improve the strength further, as well as its other properties. No? So it is weldable, meaning you can do welding. No? And it is a quench and tempered low alloy steel. No? So as far as I know, there is if ever there is, it is in very small production, no, amount of alloy steel here in the Philippines. So the ones that we produce are normally among these two, with the carbon steel being more popular. No? So these are some of the commonly used structural steel that we use in analysis and design. So during the course, we will be more confined to these three. So A36, A572, and A992. So these are the expected minimum required material properties. So the yield point, the tensile strength, the ratio, and the elongation. No? So we will discuss more about these properties later on. What are the significance of these properties? Okay. Any questions so far? Okay, so for now, there's no questions. So before I proceed to the next part, let us watch this video from AISC, entitled Manufacturing of Structural Steel Shapes. So let me share a video. No? So let me share a video. Do you see the video? Do you see this one? All right. So just check if you hear the audio. Okay. So if there are some issues with the audio, just tell me in the chat box. Okay. So let me start playing the video. It's around 25 minutes. No?
Hello, everyone, and welcome to AISC's Night School, Steel Construction from the Mill to Topping Out. Tonight is October 22nd, 2018, and this is Session 2, the Manufacturing of Structural Steel Shapes, presented this evening by Jim Schoen and Shane Vernon of Nucor Yamato Steel. My name is Brent Liu. I am with AISC's Continuing Education Group, and I'll be moderating this evening's presentation. I want to introduce this evening's speakers, Jim Schoen and Shane Vernon of Nucor Yamato Steel in Blytheville, Arkansas. Jim is a plant metallurgist and has been in steel manufacturing for 34 years in special bar quality and structural steel plants. His responsibilities over the years have included melt shop metallurgist, rolling mill metallurgist, and quality assurance supervisor. Jim served on ASTM, ABS, AWS, and AISC committees. He's a graduate of the University of Missouri-Rolla with a bachelor's degree in metallurgical engineering. He will be our second speaker this evening. But we'll start things off tonight with Shane Vernon, who is also a plant metallurgist at Nucor Yamato Steel. Shane is active with AWS, including AWS D11 and D1M. As a committee member, he's a certified welding inspector, and as well, he has been part of the ASTM A102 committee member. He has 24 years of steel industry experience. Shane?
So I paused this video for a bit. No? So if you observe, no, I tried to turn on the subtitles for this. No? However, I observed that the auto-generate. So originally it has no subtitles, so but the auto-generated captions by YouTube are not exactly grammatically correct. So that's why I turned it off. Okay. So just try to listen more carefully. Okay. So although you cannot understand much about this, no, for now, you may replay it on our module. Okay. So let me carry on with this one.
Thanks for being here, and I'll let you take it from here.
Thank you, Brent. Hopefully everybody had a happy Monday. We're excited to take you through this presentation on manufacturing structural steel shapes. We're going to do a little bit of chemistry, a little bit of process steps, and Jim is going to finish up with some metallurgy. So I'm going to present the first half. So with that being said, let's go ahead and advance to the next slide, please.
Hello, everyone.
And here we're going to go over the process overview, and again, we're going to wrap this up with some of the grades of steel that we produce. When you look at a big 1,000-yard picture of this, we start in the scrap yard, where we load our raw materials into to be prepared to be charged into the furnace. Then we go into the EAF, electric arc furnace melting. We go into that, and we make the scrap liquid, and we'll take it next to the LMF, the ladle metallurgical furnace. We perform the refining and alloying of the steel. After that process step is complete, we go to the caster, which the primary function is take the liquid steel and cast it into a solid semi-finished product, typically beam blanks or blooms. Those are then reheated in the reheat furnace to the rolling temperature. And we bring it out into the mill and we roll it in the rolling mill stands. And once it's cooled and gone to finishing and cut to finished length, we will do some testing. And that will take us to the next slide, please. So how do you define structural steels? For us, we describe it as side for bar size shapes. For most structural steel products produced in the United States, carbon is your 5 to 10 carbon range. We typically talk in points. We call it 5 to 10 points of carbon. This low carbon content is very good for toughness, ductility, and weldability. Of course, math, you get a little bit about 97, 98% iron. Some of the key elements, and we're going to explain what they are and how they impact the steel properties that we're going to go over tonight. Chromium, copper, manganese, molybdenum, typically just call it moly, nickel, niobium or columbium, nitrogen, phosphorus, silicon, sulfur, titanium and vanadium, and also tin. The next slide, please. So a little bit of an overview of the key elements that impact the properties of structural steel. So as the amount of carbon present in steel increases, of course, the steel increases in strength, but also you lose ductility and somewhat lose your toughness as well. So carbon in steel comes from both the scrap and from coke additions we put in the furnace, the ladle metallurgical furnace. And primarily we keep it low because of its adverse effect on toughness and weldability. And we'll explain that in more detail. Next element that we're going to talk about is silicon. Silicon is a deoxidizer. We add that to take out the oxygen that's present in the liquid steel when we melt it. So it's just primary deoxidizer in structural steels and alloy steels. It has a different use, but we're going to limit our discussion tonight just to structural steels. On the next slide, talk about manganese. It's the big hitter right below carbon. So after carbon, it's most widely used alloying element. It increases the toughness of the steel, improves the strength, typically has approximately a 1/6 effective ratio compared to carbon as far as strengthening. It does have a processing effect of taking care of the sulfur that's in the steel, so it improves the surface of the steel when it's rolled. But manganese, I'm going to talk a little bit about this. The balance of all these alloying elements always affect the CE, which is the carbon equivalency, as it affects weldability. And we're going to discuss the CE formula there at the bottom. And if I would, I'm going to go to that right now. That's the CE formula. It's in the A992. Basically, what CE does is gives the user an indication of what the heat-affected zone hardenability will be and can potentially lead to cracks. So we look at those alloying elements and try to balance strength and weldability and ductility and all that. Of course, heat-affected zone cracking is also affected by the cooling rate of the steel, the preheat, the filler metal. But for us, primarily, we control it. Our portion is controlling it by the chemistry of the steel. So as we look at chromium, it improves the corrosion resistance of steel. It's a mild strengthener. You'll see this in A588, which we'll discuss in a little bit. And it's a negative effect to the weldability. So on the next slide, please. Talk about copper. So copper, typically in structural steel, is a negative element. Is residual element is in the steel when we melt the scrap, unless you're talking about 588, where we purposely add copper to improve the corrosion resistance of the steel. Nickel is a mild strengthener and hardener. It's also improved the toughness of the steel. Nickel is added to structural steel shapes. It usually comes from the scrap. We typically don't add this in structural steel. Moly increases the hardness, strength, and wear resistance of our steel. And again, we don't add that intentionally in structural steel. It comes through as a residual from the alloys. And all these elements are contributors to the carbon equivalency formula that we discussed earlier. Next slide. So, in general, copper, chrome, nickel, and moly are considered residuals. They just come through our scrap, they get melted in, and they're just present in steel. We don't typically intentionally add those. And the residual amounts, they increase the yield and tensile strength by 3 to 4 KSI. We get a little bit of kick from them. Next slide. Now, vanadium and columbium, nitrogen, we bring those up together because they're all tied together. These are called microalloys. And vanadium strengthens steel mostly through grain refinement by making vanadium nitrates. They precipitate out when the steel is rolled. And it also counts against your CE. Columbium, niobium, same element. We typically use columbium as a term here in the United States. But it makes columbium carbides and nitrides. And again, it affects the final grain size of the steel after rolling. Now, nitrogen, which is an element that's in the steel, it's just dissolved into the steel from the air, atmosphere, and it's used in combination. That's what vanadium grabs a hold of, that's what columbium. They'll combine with that to make the nitride, which precipitates to the grain boundary, which makes the fine grain steel. Next slide. So, phosphorus. Typically, phosphorus is an undesirable impurity in non-piling structural steel shapes. We do our best to minimize that. There is one exception, ASTM A690, it's a marine environment piling grade. Is a case which a phosphorus is added intentionally for corrosion resistance, but it negatively impacts toughness. And sulfur, again, sulfur is something we try to get rid of in the steel. We try to process that out, and we'll explain that. And it's an impurity, lowers the toughness of the steel. And it's removed by adding lime and spar at the ladle metallurgical furnace to be removed. And we'll explain how that process goes next. Next slide, please. So how does this all pertain to the engineer? Let's look at his MTR. Again, we live and breathe by this in our world, but top requirement here, kind of give you a table looking at the different things. A little bit busy. It looks complicated, but really it's not. There's only certain key elements that you need to understand and focus on. And we'll go through those now as we go through the processing later. But ASTM A992, the typical wide-flange structural steel grade, A57250, you'll see that. You got the A588 grade B. Thank you, Brent. And then, of course, A36, the old standby. As you go down to the next line of the table, we start talking about carbon. So if you look at those, they're fairly consistent. It's got 0.3 carbon max. So the spec allows us to go higher. We typically don't run in that range, but we're allowed to by spec. And we'll bring it up. Typically, we like to get our strength from our microalloy additions instead of by carbon because we want to have a steel that has a satisfactory Sharpie B notch. So then we look at manganese next. That's a big one. It's a big addition. It's the biggest component of the alloying that we add in. So if you look at 992, it goes from 50 to 160. I'd dare say you're definitely about 1% on most stuff. Same with 572 and 588, about 1%. 836, you don't have to achieve the same strength levels. The manganese is typically lower. In the next line, we'll talk about phosphorus. This is where they're not alloys on this one. These are actually held to minimums. We don't want them getting out of hand and affecting the property of the steel, so the spec puts a max on them. So we have to stay under an 035 for 992, which is a little more restrictive than the rest. And the rest of them are at 040, which is pretty much a standard phos level. If you look at sulfur here, same thing with 992. It's a lower sulfur. That's done intentionally to help the properties of steel, especially Sharpie V-notch. And then 572 or 050, 05 max. So those aren't added. Those are residual. We try to minimize those in our processing. Silicon, again, it's just a deoxidizer used to kill the steel. Got about a 40 max on 992, what it is. And then a range of them on 15 to 40 on 572, 588, 836 is 40 max. Again, just got to have enough silicon to take care of the oxygen that you add in the steel to make it a killed steel. And we'll talk about that again. We're going to keep bringing these up so that the idea of the topic gets transferred correctly. Now the next one is vanadium. That's our microalloy addition. A little bit of vanadium goes a long way. Same with columbium. It doesn't take much to have a dramatic impact on the properties. So you look at these are pretty low numbers, 15 max, 10 max, 5 max. So these are very little additions to these make a dramatic impact on the properties of the steel. You look at copper. Copper, again, is a residual. We try to keep that down. A992 has a .60 max, 588. Now, this is where it's a little bit different. 588 is weathering grades. Copper must be within a range to maintain the corrosion effect, the corrosion protection that we're trying to put into the steel. And you look at nickel, again, it's a residual in all the other ones but 588. Sometimes we add that to get the corrosion index number up. And chromium, 40 to 70 on the next line. On A588, again, we got to hit that range. We got to hit 40 to 70 to get the properties of corrosion. Otherwise, we try to keep it down. Molybdenum, again, it's a residual. We got to minimize that. Get too much of that, steel gets very, very brittle. And we control that through our scrap recipe. We talk about nitrogen. That's just, again, that's so many ppms that we get in the steel making process. We test it on our analyzer. We'll talk about that later. But it's not specified, but it's present in the steel. Then we talk about maximum carbon equivalent. We kind of talked about that, how certain grades, 992 specifically, has a max carbon equivalent that we need to have. That's there to make sure the weldability of the steel is consistent. The rest of them don't have it specified, but it's probably specified supplementary, but it's not in the spec. Go to the next line, it talks about corrosion index. That is unique to A588. That's a calculation based on the chemistry of the steel. We have to hit this number, 6.0 or higher, to ensure that the corrosion resistance of the steel is termed a weathering grade. And again, we got the tensile strength. The big things we worry about: tensile, yield ratio, elongation. Those last 4 items there. I mean, I'm sure all engineers are pretty well familiar. Tensile strength, 65 KSI, typically all the way across. Yield strength, which 50 KSI is typically where all these products are produced at. Unless it's 992, which has a range and has a yield to tensile ratio for seismic reasons. We want to have enough ductility in the steel, energy absorbed before fracture. So that's why that's written in there on that one. And it's interesting on the bottom, the elongation there, all pretty well consistent, 18 to 20s, which I consider a fairly ductile steel. Next, please. A new grade that's coming into the market that I think is a really unique, pretty innovative product. It's been out there for a while. It's really coming onto its own. We're seeing it specified more. But it's A913 quench and self-tempered steel. And the first thing is you look through the requirements because it's got different grades, 50, 65, 70. But look at that carbon max. You can see it, you immediately see a difference right away, right? You got a 12 max versus roughly 20 that we saw on the other page. That's significantly lower. The manganese are a little bit higher because the carbon's lower. And then you look, the phos and sulfur are much more restrictive. Silicon's about the same. Vanadium, columbium, standard grain refiners. Copper's all right, about 45. And the residuals are also restricted. But as you go all the way down to the bottom where it says max carbon equivalency, about towards the bottom third there, that is, you can see where the weldability of steel comes into play, and this is actually set by specification, a 0.38, a 0.43, and a 0.45. So as you go through that, you see that as the strength goes up, we got to bump the CE up a little bit. But as the tensile strength, yield strength all go up, we're achieving this not through chemistry, but through basically the quenching of the steel, allowing it to self-temper. So you'll have a steel with the weldability of an A992, grade 50, but the properties will be similar to a grade 65. So this is a pretty innovative way of using basically a modified heat treatment process in process. This is done while we're rolling, and impacts properties that gives us a much more ductile steel, a much more weldable steel, and with no more alloy content that affects the weldability of the steel. So pretty exciting stuff. And this one's unique. It actually has a Sharpie V-notch. It's specified by the spec, the very last line, and that's unique. You don't see that everywhere. That is unique to that grade. So basically, you're mandating a certain level of toughness in the steel. So that's an innovative process in that, or aspect of that grade. So we move to the next slide, please.
All right. Thanks, Shane. We're having a slight technical difficulty here. If we could pull into a quick private speaker conference so we can get that resolved. Thank you. Please stand by, everybody.
You're with your audience. Please continue.
Okay, so just some note here. No? So this video is actually a recording from another conference by AISC. No? That's why if you also observe there's if there are some difficulties, no, they also get kind of stop. No? So okay, so let me resume.
All right, thank you, Keith. Go ahead, Shane.
Okay, Brent, I think we've now finished that slide, and we'll go ahead and move to the next one, please. All right, now we're going to start going through the electric arc furnace and operations. Again, we're taking cold scrap, ambient temperature, and we're going to get it up to 3,000 degrees F. So there's several, beginning of this process is with electric arc furnace. We're going to charge it with scrap, and then when we get done with it, we're going to tap it into a ladle, which is basically a pot that's refractory line that basically is a carrier unit for carrying the liquid steel from one process to the next. Next slide, please. All right, so this is where we come into the recipe of how we make our steel. So there's different types of scrap, and we purchase them at different price levels, and there's efficiencies of using one versus the other, but I'd like to just kind of briefly go through the different type of scrap we're going to see. In the back left-hand side is the number 2 shredded, which that's all your old combines, cars, and everything that goes through a shredding facility, and the non-ferrous product is separated off, and the ferrous product goes to us to be melted. The benefit of this is it's very dense, loads very well, and the copper is sorted out typically not through the non-ferrous separators. We don't have as much copper coming through that scrap. And in the front left, again, we go to number 1 heavy melt. It's our primary scrap type. Another primary scrap type, I should say. That's a premium product. It's very dense, very heavy, typically very clean as far as residuals. And then on the right-hand side, the lower right, is the plate and structural steel. That's just your demolition buildings, things like that. Anything that used to be an I-beam, we buy that. It's big, it's heavy, it's dense, but typically has a little bit higher residual level than the number 1 heavy melt. And then the number 2 heavy melt is basically everything else. It's your bicycles, washers, dryers, everything else that goes in the scrap supply chain. That's what we use there. And it typically has a little bit higher residual level than the other ones. And typically, the lower the residual, the cheaper the steel is. So if we move to the next slide. So the scrap buckets are loaded by a crane on the outside, and we use a blend, basically a recipe. And in that recipe, we're trying to get the residuals as low as we need to make the product we're trying to, and achieve the optimal melting efficiency. Next slide, please. And here we should have a video. Brent, if you could start that, please.
There's no sound on this video. Just so
and again, we just have a mobile crane that pushes the bucket around and picks up from various piles of scrap and just loads it per recipe. There's load cells on the bottom of that car, so the operator knows how much he's loading at any given time. All right, go ahead and advance to the next slide, please. So what is the electric arc furnace, and what are we talking about here? So this is a little diagram schematic of what electric arc furnace is, and it has multiple components. What I like looking at is a big three-phase welder. And these big graphite electrodes conduct the arc plasma between all the 3 phases and creates an incredible amount of energy and heat. Well, to contain this, we have a refractory roof that swings off so we can put the scrap in with the electrodes. We have water-cooled panels in the upper half of the shell that basically take some of the heat away so we don't melt the furnace down. And then there's the bottom half is all refractory lined with dolomitic type refractory. The scrap is in the middle. We have a slag door on the one side that the slag goes out and we'll talk about what slag is later on. And then we got the tapping spout or the tap hole on the other side where the liquid steel goes when we're done melting the scrap down. So let's go ahead and advance to the next slide. So the roof and electrode raise up to swing out for a charge. Go ahead and advance to the next. We bring the charge bucket in, and we bring it into the furnace and open the clamshells and drop the scrap in. So next slide, please. Here you see a picture of it trying to, sorry, I got a little error in here. Dropping the scrap into the furnace, and you see the fireball coming up. This is probably the most neatest part of the process, but the scrap goes in, and quite a reaction there. And go to the next slide, please. And I believe we have a video here, which is live, and I'll go ahead and play that, and I won't talk through it.
Okay, so that's pinakita niya lang kung how the scrap metals are being melted na. So we go back to the video. So uh, we go back now. So he just explained the chemicals that are involved aside from iron and carbon. And then he also gave us an overview on the process of the steel making. So like from scrap collection down to the melting, down to, although the entire process was not shown, no? But in the very first part of the video, nagpakita sila ng some sort of a map as to how the structural steel is manufactured. No? And then once you have the scrap, you introduce other chemicals, and then you do some heat treatment, and then you do some rolling or finishing process, and then there you go. No? So is another thing that it was pointed out there is yung differences between the structural steel grades that we use, like A36, A572, A992, all of those, no? And then in the United States, there's an emerging structural steel grade like A913, although I don't think it is still available yet here in the Philippines, no? So the utilization of scrap is also highlighted here. So as you know, we do not just melt the scrap metal that we collect. No? So they sort it out first, depending on the type of the scrap that they have, and then they also sort it depending on what are the materials present in that scrap aside from iron or steel itself. May mga impurities yan, like for example, kung painted yung metal, that paint is an impurity, and so on and so forth. And then upon collection of scrap for the production process, we do not just use one type of scrap. So in fact, if you see the video, we mix different types of scrap, no? In order, so the reason for that is to to attain more easily the material properties and the chemical composition that we want. Uh, that's why we, instead of just using the scraps randomly, we do some scrap blending. Uh, and then the process goes on until you produce structural steel. Okay? So, do you have any questions so far? Wala? Okay, so far there's none. No? So we are already familiarized with the how what is structural steel composed of, what are the processes that we do to manufacture steel, structural steel, and what are the common structural steel grades that we use. No, so it depends on the so the difference lies on the material properties which are derived from the chemical composition of the of those steel grades. No, so now we also try to learn how structural steel is classified according to its cross section. No? So generally, structural steel shapes are classified into two. We have the hot rolled sections and we have the cold form sections. No? So we will first discuss the more common structural steel shape that we use here in the Philippines, which is a hot rolled section. So when we say hot rolled, it means that it goes through the process of rolling and heat treatment as it is. So the usual manufacturing method for structural steel, they produce hot rolled sections. Okay, so we have different types of hot rolled sections. So I will go through this one by one. No? So geometric properties of these sections may be looked up at 2004 ASEP Steel Handbook. That's why you need this. Okay. Or in United States, the one they usually use is the AISC Steel Construction Manual. However, in the Philippines, uh, we use this one more because it also lists the sections that we normally use here in local practice. That's why it is more favorable in this class to use this one. Okay. So what are some of the hot rolled sections that we produce? So the most common are what we call the I shapes. No? So I shape, we call them I shapes precisely because it is shaped as letter I. So we have two different types. We have the wide flange sections and we have the American standard beam sections. Okay. So first we have the wide. So what is the main difference? What is the difference between wide flange section and an American standard beam section? So the main difference is the length of the flange. No? So as we know, an I section is composed of two flanges, this one, and a web, which connects the two flanges. Okay. So the main difference between a wide flange section and an American standard beam section, again, is that the size of flanges are different. So in the case of wide flanges, the flanges are wide flange sections. Rather, the flanges are longer, but they are normally thinner. No? It has less thickness. In standard beam sections, the the flanges are normally shorter, but it has a larger thickness. No? So in actual, we have a standard American standard beam sections have sloping inside face for their flanges. No? That's why they are thicker than the Y shape. Yeah. So we usually use this in several types of structural members, like for beams, for columns. No? So usually for frame members, we use I shapes. No? So how do we distinguish if it is a wide flange or a standard beam section? By naming. So the naming for the wide flange is W. That's why we also call them W shapes. For the American standard, we use the letter S, no? From the word standard. No? So we also call this S shapes. Okay. So how do we differentiate? How do we name these sections rather? So for example, we have W18 by 50. What do the numbers 18 and 50 mean? So the notation for the naming of the I sections now is the type AXB. So it follows this format. Same thing with S. So what does A stand for? So this in this case it's the 18 right here. So A here stands for the depth of the shape in inches. So in this case, if we have a W18 by 50, it means that the depth of the section is more or less 18 inches. Okay. How about the other number here, 50, letter B here? B stands for the linear weight or the linear mass of the shape in pounds per foot length. So for example, W18 by 50, if you have 1 foot of this section, meaning it weighs 50 pounds. So if say you have a 6 feet of W18 by 50, you can estimate the weight of that beam, of that member. So it would be 50 multiplied by how many foot, which is 6. It would be around 300 pounds. No? So that's what these numbers mean. Same thing with the American standard, the notation is still the same. So the first number is the depth, the second number is the linear weight. No? And take note, we are naming this, we adopt this naming from AISC, so meaning they are always in English units. No? Although the ASEP handbook provides the values in metric units, but they name it the same as for the United States, the using English units. No? So you try to browse some parts of the steel handbook in order for you to be familiarized. Okay. So then we also have some miscellaneous eye shapes. No, the eye shapes that do not usually belong to this two. So we usually name them as M, and the notation of the nomenclature of the section is also the same as that of the I beams of the other eye shapes. Okay. Aha. So next one we have the standard channel, the American standard channel. We also call them channels, no? So C shapes. This one are typically used in trusses, no? And in roofing systems, no? We usually use them as purlins, no? So the notation here, so we call them C shapes also, no? So we denote them as C. The notation here is pretty much the same as that of the I shapes. The first number is the depth, the second number is the linear weight. Okay? So here's what the channel section looks like. Next, we have the angles. So angles are L shapes. No? So they look like this. No? So generally, we classify angles into two, either equal leg angles or unequal leg angles. When we say equal leg, both legs have the same length, while unequal leg angles, they are different. The legs have different length. No? So the notation or the nomenclature for angles We call them L shapes because it is shaped as the letter L, no? Obviously. So we denote it as L. And then we have three numbers here now, A, B, C. So the numbers A and B are the leg dimensions in inches. Usually, in case of unequal angles, we go with the longer leg first. So, for example, L 6 by 6, meaning the leg dimensions are both 6. For unequal, L 6 by 4, meaning the leg dimensions are 6 and 4. Okay? But how about C? What does this third number stand for? C stands for the leg thickness. So the thickness of both of the legs. Usually they are uniform, no? So we do not see an angle where the thickness of each leg are different, no? So in this case, L 6 by 6 by 3/4, meaning the thickness of each leg is 3/4 inches. While for this one, 6 by 4 by 5/8, meaning the thickness of the leg is 5/8 inches. Okay, so that's how we name angles. Okay, we also have what we call structural T's. So structural T's, from the name itself, are just T shape, no? And usually these sections are derived from I sections. So the I section, you just remove the other flange, uh, then you would have now a WT, a structural T. Okay, so it may be named as WT, ST, or MT, depending on which I shape does that structural T come from. Uh, so in this case, if we say WT, it means it comes from a wide flange rather section. If we say ST, it comes from the American Standard Beam section. For MT, it means that it comes from the miscellaneous I shapes. Okay, so in this case, we have a WT example. So the A and B here, it is pretty much the same as that of the I-beam. A, the first number is the depth, the A, and the B here is the linear weight in pounds per foot. So structural T's are usually used for chord members in trusses, no? So the bottom chord or the top chord, no? So because it is easier to connect the other truss members like this, no? So that's why they use them for chord members. Okay, you do not normally use this for say frame members, no? It is very rare to do so. Okay. Next, we have the steel shapes, hollow structural sections. Now we call them HSS, no? From the initial letters of the name. So we also call them as structural tubes or structural tubing. So these are normally used for pleasing architectural appearance. So the usual detail for this one is you erect this one and then you pour concrete inside this. No, so uh, doing that would result to lower formwork costs because you do not need temporary formworks anywhere. You do not need some plywood or phenolic board. No? This would serve now as your permanent formwork. No? So notation here, so we call them HSS and then this one, so ABC. So in case of rectangular or square hollow sections, A and B stands for the outside sections, no? So the length and the width, okay, in inches. So usually, like the angles, we denote the longer dimension first, okay. And C here is the thickness of the section, the thickness of this of all of the sides of the hollow section. Okay. For circular tubes, we denote them by their diameter and by their thickness. No? So that one is a bit different. No? But for rectangular or square sections, we use this one. Okay. And then we can also do some combination shapes. So it is a combination of different shapes such as angles, channels, and eye shapes. So there are cases where one section is not enough and you have some limitations when it comes to the use of the shape. So you usually do combination shapes. So for example, we may do double angle. So meaning you have angle here and you have an angle on the other side. So that is considered as one member. One member, but it has two sections. No? So same thing with the channels, or a channel and an angle, you may combine them. No? So you can also some examples of combination shapes in CSiSteel handbook. Okay. So and then we have some miscellaneous shapes. We have the bars, so solid bars, no, plates. So especially for connections. So we denote them by their width and by their thickness. Pipes. So, and we have the so-called built-up sections. So built-up sections, you just use plates to form some of these sections. So for example, you want an eye shape, but the type of eye shape that you want is not readily formed like this. For example, you do not want 18 by 50, you want something larger, but it is not produced in a factory. What you do is you use plates to assemble the eye section that you want. So assembling a section using plates or existing standard shapes, we call them built-up sections. So we usually use them if there are some requirements or conditions to be fulfilled, or due to actual material requisition conditions. So for example, you are very far from some factories that produce the section that you want. You had no choice but to go to a nearer factory. You order some plates and then you build them. You build them up. You make some built up sections. Huh? So that's one. That's what built up shapes are for. So how are these plates connected? For example, so we use welding. Huh? We do some welding to connect these plates or these shapes in order to form a larger shape. Huh? So usually we label them the same as this depending on what you have formed, but with the letter B. So for example, you want a built-up W shape, you denote them as BW. So again, ASEP handbook also provides some properties of common built-up shapes. No? So we denote them as with the letter B. Okay. So do you have some questions so far about the hot rolled sections? Okay. So, sige. So these are some examples of hot rolled sections. No? So again, hot rolled sections are produced by uh, by having a heat treatment. No? So the normal manufacturing process of the of structural steel, we produce hot rolled sections. So another type of structural steel sections is what we call the cold form section. So what you do is you only need thin sheets of steel and then you bend them without applying heat. You bend them into these shapes. No? So you have a sheet of steel, and then you put them into a forming machine in order to form these shapes without application of heat. Okay. So the main advantage of the cold form steel over the hot rolled steel is that you it is more versatile because you can form more sections, no? Compared to hot rolled sections where it only has standard sections, no? And in some cases built up sections. In cold form steel, you have more freedom as to what shape do you want. Okay, and at the same time increase yield strength. So disadvantage would be limited applications and reduced ductility. So in the Philippines, we only use them for light structures and as well as for walls and roof purlins only. We do not mainly use cold form steel here in the Philippines for larger structures, no, due to seismic reasons, no. So although in some parts where seismic activity is not significant, we can use cold form steel. But in the Philippines, where most of the country is in zone 4, cold form steel is not really used. No? However, it is also cold form sections may also actually be used, no? In high seismic in a seismically active area. So in the United States, no, more especially in California, cold form steel has an increasing popularity in use. No? So there you go. No? So I think if you have attended some seminars last year, no, a company presented some cold form steel. No, the name of the company was FrameGo. So they are the ones doing recommending cold form steel for structures here in the Philippines. However, they limit their application to residential and commercial na low story. Okay, like one to up to three floors, I think. No, so there you go. So there are also geometric properties of some of these shapes. Some of the common cold form shapes may also be looked up to at the handbook. No? So, however, in this course, we will be concentrating more on the use of the hot roll shapes rather than the cold form. No? So, the design for cold form steel, no, is entirely different one. No? Although the very concepts are the same as what we discussed here, however, the design formulas are a bit more different. Okay, so we will not discuss the use of this one here. No? So I introduce it here just for familiarity, but we will be focusing more on the use of these sections right here. Okay? More especially the I sections, because this is the one of the most commonly used sections. Now, okay, so those are the two types of structural steel shapes that we may use in construction. No? So again, in this course, we will be focusing more on the use of hot rolled sections. Okay. So now, we can, for example, if you do not have a copy of the 2004 ASEP handbook, although I recommend you having a copy of this one. Okay. There are some applications that you may also use. So we have the AISC dimensioning tool. So it shows the dimensions of the common hot rolled sections. Excuse me. And then we have CSiSteel and CSI sections. So these two are Android applications. Now for those using iOS, you may check if these are available. Okay, but for Android, surely these are available. Okay, so let us check some of these tools. No, So first, we have the AISC first. Okay. So this one, no? So what? So it gives you the dimensions that you want. So like the width, the depth, the flange thickness, the this dimension, the dimension T, no? The web thickness, the half web thickness, the K depth, the K1, and the workable gauge in case you are putting some bolts here. So there is a minimum distance from the edge to the center of the hole. No? But we will discuss that on later lectures. Okay. So for example, you want W18 by 50. So you select here W18 and then you pick W18 by 50. Those are the dimensions. So it also gives you the area, the nominal weight, and then the dimensions here. So all of these are in inches, as denoted here. Okay. So the only disadvantage of this one is that it does not give you the other section properties like moment of inertia or plastic modulus or section modulus. This tool does not give you that. Only the dimensions. No? So, for example, you want other section like say a channel section, for example. So you have a channel here and say you want C6 by 6 by 1 half. So you select C6. So C6 by 8.2. So for example, there are your dimensions. Okay. How about angles? So you just select L and then say you want L6 by 6 by 1 half, for example. So you select L6 and then 6 by 6 by 1 half. So this one, there you go. Those are the dimensions. Okay. So that's how you use the dimensioning tool. So you have all sorts of sections here. No? So you just have to do some clicking in order to produce this one. Okay. So that's how you use the AISC structural steel dimensioning tool. This one is located in their website. So you just have to click the link in the Canvas module that we have. Okay. So next, I'll just show you the Play Store page for the CSiSteel. So this one. So do you see? So this one is for steel sections. No? So these are some of the screenshots. No? So at the very first part of the app, as you open it, there will be some types of sections. And if you want to save some specific sections, you may save them, you may bookmark them. And then, for example, you select a structural T, you may select it here, whatever section you need. And then it gives you the diagram and the dimensions. No? So, and at the same time, it may also give you some other section properties like the moment of inertia right here, the area, no, etc. Then for pipes, and they tested it in different types of devices. So we have dimensions, the section properties here, the location of centroid, the moments of inertia, the radius of gyration, the torsional constant, all of those. No? Okay. So another feature of this application is that you can convert them readily to SI. So for example, the default unit is the US units, USC. You may convert them to SI. You just click it here and then you just convert the units. No? So that's how you use CSI still. Okay? So uh, we now have the I will now present the CSI sections. Okay. So here, this one is more general. No? So especially if you want some built-up sections, no, you can use this one. So the difference between CSI sections and CSI steel is that CSI steel is only for mostly for hot rolled sections, no. But CSI section, you can use any section. So if you want a rectangular, tube, trapezoid, you have a T section, I section, you have circular, no? All types of shapes, you may use it here. So apart from that, apart from the selection, the same properties would be produced, like the dimensions, no? And the other area, the other properties like the moments of inertia, the torsional constant, the centroids, uh, and it may also give you the calculations. So there you go, no, the selection of the sections that you may use. No? So here, for example, you want a rectangle, you can just also input the dimensions. No? So what is the height of this one? What is the thickness? No? And then once you input the dimension, it gives you this. Okay. So that's one example. No? So they tested it also in the different devices. Okay. And then another thing here is you may also you may change the units in which you work on. So for example, you want SI units, you just have to click the three dots here and then you change the units. No? So that's how you use CSI sections also. So CSiSteel and CSiSections are both developed by the same team, Computer Structures Inc. No? As far as I know, this one is the same company that develops ETABs. No? So it's good that they also produce these types of applications. No? So those are some alternatives. No? Those are some alternatives that you may use. Okay. So these are some alternatives that you may use in case you do not have a copy of steel handbook or AISC steel construction manual. No? However, I still recommend using this one for us to be more consistent in units, because I observed that if you use either of this, there are some deviations or some differences from the values presented in the steel handbook. So in that case, I will be leaning more on the use of the steel handbook. But if you had no choice, you do not really have a copy, you may use this. Okay, you may use these applications. No, but again, you take note of the difference in the values. Okay, although the difference is not much, maybe within the range of 1, 2. siguro malaki na yung 5 mm, no? Up to 5 mm difference, no? So that's that's what you have to take account, no? That difference. Okay? So that would be all for the steel shapes. Huh? So do you have any questions? None so far? Okay. So okay, we will just take a 30-minute break. So it's 9:15 already. So you may go back at 9:45. So quarter to 10. Okay, then we will just finish the discussion of the last part, which would be the material behavior of steel. Okay, so you may log out of this conference for a while if you save some data, but do not end. Huwag niyong i-end. Okay? So, ayun lang na. So, sige. If you do not have any more questions so far, so you may take your 30-minute break.